Hey everybody, this is Bharat Muthuswamy.
And Amir Mukhdari. This lab is on filtering signals based on their frequency.
We will analyze the circuit shown here and determine the frequency response of the circuit. Notice how we specified the ratio of V out to V in as a complex function of angular frequency omega.
Note also that the units of angular frequency are radians per second. Omega is 2 pi f, where f is the natural frequency in hertz. We need to remember this because our function generator uses natural frequency. That is, frequency is output in hertz. And this is a common source of error for the novice EX40 student.
Amir has made an excellent point. Let us first understand circuit functionality in terms of frequency.
That is simple enough. Given our circuit, the frequency-dependent impedance of the capacitor is given by 1 over j omega C1. Hence, at low frequency, the magnitude of the capacitor impedance is infinite, or infinity. In other words, the capacitor acts like an open circuit. Hence, the capacitor in the circuit blocks DC or low frequency. I have heard of expressions like capacitor in the current path blocks DC. So this is what it meant.
Correct.
Okay, at high frequency, the magnitude of the capacitor impedance is 0, and hence the capacitor acts like a short circuit. So the circuit is essentially a high-pass filter.
Exactly. So, the moral of the story is before you begin any frequency analysis problem, it will be extremely useful and intuitively helpful to quickly check circuit behavior at DC and at very high frequency.
Now that we have an idea of what the circuit does, don't we simply convert circuit into frequency domain and just use the op-amp golden rules in the frequency domain?
Yep. So go ahead and finish that derivation.
Okay, here's a representation of the op-amp circuit in the frequency domain. Applying the op-amp golden rules and simplifying, we get this result.
Okay, so if you look at this result, it basically says that V out over V in is negative R2 over R1 plus 1 over j omega C1. My point is, if you look at the magnitude of the capacitor impedance as omega goes to infinity, you will see basically from this expression you're going to get V out over V in is minus R2 over R1. We encourage you to rewrite this complex function here in terms of, let's say, magnitude and phase, and check if as omega goes to 0, the capacitor acts like an open circuit, and as omega goes to infinity, the capacitor acts like a short circuit. Okay, now for the usual multisim and lab demo. I'll be doing the multisim demo and Amir will be doing the lab demo. Okay, so here's my simulation. I've already run it once, so let me run it again. And you can see with an input frequency of 1.5 kilohertz, amplitude of 1 volt peak to peak, basically I'm getting a 180 degree phase shift between the input, which is in red, and the output, which is in blue, and that makes sense because at really high frequency, the gain is negative R2 over R1, or the circuit is acting like an inverting amplifier. Let me now reduce the frequency. So I'm going to go down. Let me make sure I do it the right direction. Yep, there it is. And if you did your theoretical calculations, you will see that around 200 hertz, the output amplitude will start decreasing. And there you can see the decrease right there from 300 to 200. Now at lower frequencies, I'm going to keep going down. It's even more prominent in there. You can see that the capacitor is, there you go. This is at 20 hertz. It's blocking DC. Okay, now Amir will do the physical circuit demo.
So here is the lab demo of our high-pass op-amp. This is our TLC 277 setup. Over here, you can see we're supplying our rails with positive 5 and negative 5 volts. We're using the function generator to give it a sine wave, 1.5 kilohertz, and the amplitude is 500 millivolts peak to peak. It's not much, but that part doesn't really matter. The frequency is what we care about most. So over here, we've plotted both input and output. As you can see, there's a 180 degree phase shift. So now what I'm going to do over here on the frequency generator is I'm going to slowly reduce the frequency until we reach our corner frequency, which is calculated at about 159 hertz. And then once we reach that, you'll start to notice something interesting happen. So right now we're at about 200 hertz. You're going to start to see the high-pass filter working its magic. And as we reduce that frequency, you can see the amplitude is getting reduced in our output. And that's how a high-pass filter works. So right now we're at about 50 hertz, and you can see we've lost about half of our amplitude.
Okay, so now that I've seen the multisim and the physical circuit demo, let's, as usual, let you work on your lab. Okay, next time we're going to be using analog to digital converters. Most signal processing is now done on computers, and hence we need a technique for converting analog to, well, digital.
See you then.